Thank you, Laurel. I'm so sorry for that. I have been talking away for ages without unmuting myself. This is just so stupid. Let me start again. I do apologise. If you've managed to follow what I'm saying, I've been talking for, 8 minutes and not been able to hear. No wonder people have left. Oh, I feel so stupid. Right, let's start again. Hello. We'll start again. Thank you so much, Laurel. I am doing the mechanics lessons now to try and help people who are maybe doing the course. They're in year 12 at the moment. Maybe they're in year 13. Because we're still, although the announcement today has been that there's no exams, we are still going to be doing a teacher assessment for all the course. So those people who have still got to do their exams are going to still need to learn all the things, and then your teacher will be able to assess them using a variety of different means over the next few months. So it's important we still learn this stuff. So what I'm going to be doing each Wednesday at 5:30 to 6:30, I'll be turning my sound on normally. I will be doing a video where I explain a topic we're talking about, but it's also a question and answer session. So, for example, I need interaction from you. I'm hoping people will join weekly, and obviously, if I remember to have the sound on, people are more likely to join weekly. I will be able to interact with people and show people how it works, and each topic I can answer questions as well. We can then do some exam questions afterwards. Now, what I was talking about, let's go back to my screen and I'll try and explain briefly what I was talking about. So here we have a wooden block. And I talked briefly about having my phone as a wooden block on here. So here's my phone, and on a flat surface, there is no friction. There is no attempt to move this block. However, if I try and push this block and don't put much force in, something stops it moving. That is where friction is applied. Equally, if I slowly tilt this up, but it doesn't move, some invisible force must be stopping it from moving. Otherwise, it would just fall. There is a chance of it moving now. Why is it not? It has to be to do with friction. So we now look at the models I've drawn here. We've got my phone drawn as a wood block. On a flat surface, I've tried to draw a flat surface, we can see the only two forces involved here are gravity, which is the gravitational force downwards, which is the mass multiplied by gravity, which is mg, and a resistant force, which is always perpendicular to the surface. So in this case, they balance each other out and everyone's happy. However, what we have here is my daughter pulling a block along, using a bit of string. She's pulling a block along the floor. This one's in the kitchen, and this one is in the lounge, using some carpet. Now it makes sense that there is a friction force going on here, and the friction force is preventing the block from moving. It might still be moving, but the friction force prevents it from moving to some degree and has energy exchange. Please, Laurel, can you confirm that you can hear me now? I do apologise for the start. We now have these friction forces applied, and we're trying to pull in this direction, and a force being applied this way, and we're trying to it's trying to cancel that out. Now, when we're trying to pull that way, the forces are going to be relevant for two things. They're going to be relevant to the surface that we're on, and the resistance offered at R. Because if something's really resistant at a really high R, as in a really heavy surface, the friction's much higher. We've all seen this. You try and drag something along the floor and it's really heavy, it's really difficult to move. But if it wasn't the case that the friction was higher, it would still be as easy to push a heavy thing. So we know this is the case. But it's also much more difficult to push things on carpet than it is on lino, because of the fact that we use this coefficient of friction, mu. Mu is the weird symbol that's used for it, and every surface has one. So whether it's ice, or whether it's carpet, or whether it's wood, there will be a coefficient of friction. For example, if I type in coefficient of friction of carpet, and it says the 0.015, 0.015. So we can come back here and I'll say carpet is 0.015. and kitchen would be the lino 0.0099. You'll see it's not that much different, but there is a difference. That means the force is always equal to mu r. So let's imagine, let's simulate this for a second. Okay, let's clear off a bit of the information on here and let's try and put real numbers in. If this is a real problem, let's imagine she's got a 5 kilogram wooden block. That's quite heavy. Let's make it a 1 kilogram wooden block. I don't want her to get hurt on it. So we've got a 1 kilogram wooden block. That means we can do the mg, we can swap out that for 1 times g is 9.8. We're going to use 9.8 as g. That means because this is not going to float into the air, the resistant force must be the same because it's not floating in the air. And what we then therefore know is that the friction force, the maximum friction force, this is going to be the maximum friction force that it will prevent it moving. And I'll explain why I've done that in a second. Is going to be 0.099 times 9.8. So we've got 0.099 times 9.8, and we get something like 0.97 newtons. If I apply 0.98 newtons in the kitchen, it will move. This is why my daughter can pull her thing much easier in the kitchen. She needs less force. Whereas if we've got the slightly higher number, it will be slightly higher the amount of force needed. I imagine this one, 0.015, and I'm aware, I think I've put not enough noughts in that first one, is 0.147 newtons, and this was 0.09 because I didn't put enough noughts in. Okay, so this force needed, because it's carpet, needs to be higher than this force. Not a big force for a 1 kilogram thing, but it's still a force all the same. Now, the friction force, the reason I referred to this earlier as the maximum friction. I called it the F max. The reason for this is there will be a point up until, let's say, my daughter manages to apply a force of it on the carpet of 0.12 newtons. It won't move. And it won't move because it hasn't overcome the maximum friction. Basically, it needs to overcome that, and at any point when it is moving, there'll be the maximum friction. If it is stationary and it is not able to move, there will only be the friction required to keep it stationary. There cannot be more friction than the movement friction applied, because you can't have a situation, go back to the thing here, you can't have a situation where the object won't move forwards and backwards. You can't have the situation where I've pulled it a little bit, but that means the friction makes it go the opposite way. That doesn't make any sense. So we can't have a situation where friction is bigger than the force I'm applying. So what this F max says is, this is the maximum friction can be applied on that surface before the object starts moving. And then it overcomes friction, we call it. Now, we can do this with another example. And I'm going to clear the screen, and hopefully you will all be able to see what is going on. I say all, the two of you who are watching and anyone who joins later. So I think I might have to edit this video, because obviously it's got quite a lot of me talking in silence at the start. So we've got a surface, and I don't know what that surface is at the moment. But on it, I have a block. Now, most objects, this could be any form of toy or thing, and they're modelled as blocks in mechanics. So again, this block is travelling. It could be a train, it could be, for whatever reason, it's travelling. It's got a mass, and we know it's like a train or something because it's got a mass of 80 kilograms. And it's travelling that way. So we can first of all apply our forces to it. There is a force causing it to go forwards. Okay? And we don't know what that force is. But we do know that we can work out the friction force that is at the back, mu r. Now this one will be the maximum because it's moving. We can then say, well, this one is going to be 80g. Therefore, this is 80g because it's not floating. And so we know we've got mu times 80g. Let's say it tells us that mu for this surface is 1.2. It's quite a friction-filled surface. So we do 1.2 times 80g is going to give us 940.8 newtons. So it's quite a strong force against this object. We can also see the force that is driving the object as long as we know the speed in which it's travelling, or the acceleration realistically. And this is because F equals ma. These are not the same. This F we call the resultant force, and it is the force once we have taken away the friction. So in order to help with this, I'm going to call this D for now, and we're going to call D is the driving force. We are assuming this is some sort of train, and we're going to give it an acceleration now of 2 meters per second. So while it's accelerating, we know the driving force, take away friction, has a resultant force that equals ma. So we can work through the problem. F equals ma. We know it's 80 kilograms, so F equals 80 times 2 is 160 newtons. However, that is the resultant force, and we've just worked out that there is 940.8 newtons dragging it back, friction force. Therefore, the driving force must be 160 newtons plus 940.8 newtons, giving us 1,108 and an extra 0 newtons. So therefore we now have a full calculation going on here of all the different resultant force. Okay? So hopefully that makes some sense. We are now going to move briefly on to a slope, because everything I've talked about so far can be applied when we're not talking about a flat surface. If I now draw my block on a slope, it stands to reason something is stopping it falling. So normally, if this is a 4 kilogram mass, we have a direct down mg. But the resistant force this time is no longer in equilibrium with that. We now have still a mu r, but we have a few more calculations to make. This is my friction force, and I've put friction in the wrong place here. This mu r should be the other place. Mu r is stopping it falling. Now again, this is where I talk about F max. You will often see questions talk about the block is at the point of falling. This is so that you can know that you're using the maximum possible friction. When it says that point of falling, the reason for that sort of sentence is it's saying any more mass and this object would move. It is balanced with the friction. It's in equilibrium right now. The friction is at its maximum point. In order to work this out, we change where we resolve. We resolve up and down the slope, and we resolve perpendicular to the slope. Now, going up and down the slope, perpendicular to slope, is the easiest one. R equals whatever this angle is, but we now need an angle, and this is found using the angle of the slope. This angle here is recreated so that we know that the vertical and horizontal components, we know that this component can be made in to a triangle where this angle is the same as this angle, and we want to know this side here. Now, we then therefore would consider this little triangle to be the hypotenuse, and the 4G is going to be the adjacent, and we know that cos, let's say that's theta as well, cos theta is adjacent over hypotenuse. We want to know what the adjacent, we want to know what the relevant angle is, so we call it 4G cos theta. Okay, so what we're trying to do is, sorry, I've made a mess of explaining this. Can you tell I've just got back from my run and I'm a little bit stressed by the fact I didn't record properly. Here's my thing. That's the hypotenuse, sorry. That's the adjacent, because we want that force. And we want to know what component that force is. So there's my right angled triangle. Hopefully you can see what I'm talking about now. And so that's why we've got 4G as the hypotenuse, which is why I've rearranged it so that A is 4G cos theta. So we can say that R equals 4G cos theta. This is because the angle, the forces going this way and that way, any force that is perpendicular is ignored when we're doing the when we're doing the resolving in that direction. So now when we're resolving the direction of the slope, we've got a value for R. That means we can now say, the only force here stopping it falling is going to be mu R, and that is going to equal 4G sine theta, because using a different colour, hopefully I can explain, in this direction of force, we've now got the hypotenuse and the angle is here, used to the Z angles, that's angle theta now. If that's angle theta, that's angle theta. Therefore, this is the opposite. So we've now got the opposite in hypotenuse, which is why we always use sine when it's in the direction of travel, and cos when it's in the direction perpendicular to travel, perpendicular to the slope. So you can see 4G sine theta equals mu R, but we already know here that R was 4G cos theta. So we can now say that 4G sine theta equals 4G cos theta times by whatever mu is. And you're in the question, you'll get given mu, you'll be given angles. We'll do now a question with actual numbers, because I can understand that's quite theoretical. I'm assuming if anyone has any questions, they will put them online. I can see I've got 3 people watching live. So if there are any questions, please do stop me. I can just go on and on. I'm trying to help it make sense. I'm aware I've made a few mistakes today and I do apologise. So we've got a slope. And another line makes this a slope. This angle of this slope is going to be 24 degrees. And on this slope, we have an object that is 8 kilograms heavy. So I'm going to immediately draw 8G going down there and a resistant force to the slope of R. We then say it's on the point of moving. Therefore, this friction, mu R, is the maximum it can possibly be. We then need to know the mu of this slope, and the mu of this slope is 0.3. it's a wooden slope and it's got a mu of 0.3. Therefore, we can now start working out the resistant forces and the friction force. So we have to go through our steps. Our first step is to resolve in the direction perpendicular to the slope. Remembering that is ignored when we're doing the perpendicular to the slope. So the only forces I can see that we've got are going to be 8g cos 24. Remember I said perpendicular to the slope we use cos. I could draw a diagram to show you again. Feel free to go back and see that. That is your value of that, and that equals r in the other way. It's not sinking into the slope, therefore this is in balance, so they must be equal to each other. Notice how I'm not actually putting the numbers in this and getting a value yet. I normally wait until the end. But what I'm now going to do is look down the slope. When I resolve down the slope, this brick block we're told is not moving. So we know that 8g sine 24, I've said that down the slope is always sine. I can draw the diagram to show you again if you need me to, very quickly. That's down the slope, that's 8g. There's my right angled triangle, that's the hypotenuse. We want that force, we want to know the component that's going that way. O and H is sine. And we know that that force is equal to mu r. But we know r. So we can now say that 8g sine 24 is equal to 0.3 times 8g sine cos 24. So we can then work these different things out. But you'll see, if you put these in the calculator, that's not true. And the reason it's not true is because I've given you all the information here. Realistically, what they'll do in the exam is not give you that mu, and they'll ask you, what is mu? So that's what we're going to do. We're going to say, well, we don't know mu. You can see, the first time I did it, I put them all in so you could see where the numbers would go. But now, if we didn't know it, this is a division, so mu equals 8g sine 24 divided by 8g cos 24. And we're going to, the 8g's will cancel out. And we end up with sine 24 over cos 24, which if you're already in year 13, you should already know is tan anyway. But we're just going to put it straight in. They've cancelled each other out, and we've got 0.45. So we weren't far off with 0.3, but you can see how you can work out the coefficient of friction given the fact that an 8 kilogram block doesn't quite slide down at a 24 degree slope. And you can then, this is how you could actually work out coefficient of friction of real life objects. If we go back to a second to my slope, I could now work out the mass of this. I could work out the angle at which it doesn't move by measuring using inclinometer. Keep going up until it moves. It's starting to move, so I'm going to go back down again. I can then, using the mass and that, I could work out the exact value of mu of this. And this is how you can compare the surfaces of different things and their friction just by purely measuring and finding out different things. Now, the last thing I'm going to talk about, I'm aware I said it would be like an hour, but because people aren't asking me questions at the moment, we're going to stick to 35 minutes, 40 minutes, unless people have questions, and then I'll leave you to go away and do the questions that are attached to it, is how can friction flip round? Well, there can be occasions where you have the same setup we've already talked about. Here's my block on a slope. But all of a sudden, at the top of the slope is positioned a pulley. And this is where things get different. I've done a lesson on pulleys. If you wanted to find out more, you can watch my lesson on pulleys. But this string, which I will have to move because it should be horizontal, is going around the pulley and pulling upwards. But because this force is pulling upwards, the block is trying to move. So there will be a friction force here if the movement is up. However, if I took some scissors and cut into that string, immediately the friction would change direction. So if the movement is this direction, there is friction against the movement. If I then cut the string, and all of a sudden the block that was going up the hill is now trying to come down, as soon as that movement changes, as soon as the movement changes to down, friction then goes to the other side. Still related to the resistance of the block and still related to the coefficient of the surface. Therefore, this force can 1 minute be exactly mu r, the friction force can be exactly applied in one direction, and just by the cutting of a string it can switch round and be the other direction, because it is always counter to the direction of movement. Wherever the object is moving, that is where the opposite direction is where the friction force is applied. I hope that's made some sense. Maybe someone could go in the chat who has been watching and let me know if they've understood anything, or if indeed they've got any questions about anything they'd like me to do further. I have put a link in the chat. Normally I make my worksheets myself, but I don't necessarily need to do that for A-level because there's some brilliant stuff out there. You'll notice in the description below the video there is a link to a video about to a page where you've got interactive maths questions. If you don't use it already, I strongly recommend all the stuff on the math solutions online stuff. So feel free to do those questions. Hopefully what I have said today will make them make a lot more sense. The few bullet points for what I've tried to go through today is a reminder. I mentioned that if you're resolving up or down the slope, then you're going to use sine theta and mg sine theta. If you're resolving that way or that way, then it's going to be mg cos theta. That's one of the things I've talked about. Friction is counter to movement. So it's the opposite direction to movement. And I've also talked about friction. The maximum friction is mu r, not the friction force, but the maximum friction force is mu r, because it may well be that it's stationary, but it is not needing its maximum friction force. I hope this has been useful and continues to be useful. I may well take this video, download it, edit it, remove the bits where I wasn't talking, and then try and put it back. I don't even know how I would go about doing that, but I'm aware that I've been an idiot. I might put some what's it called, subtitles over the top saying, please go to this number to see me actually talking. Thank you for bearing with me. I promise you next week I will try and make sure that I keep the sound on, and hopefully friction has made sense. If anyone's got, in the meantime, before I put the timetable out on Friday and Saturday, a topic that they would like me to go through in full from the A-level mechanics, please let me know. If not, I will choose something that from the mechanics course and we'll go through it. This will start being an hour if we have enough people to ask me questions and who want to sort of find out a bit more about stuff. But while I haven't got questions, it will just be obviously me talking until I think I've covered everything. I've been Mr. Harris. You haven't. Look after yourselves and take care. Goodbye.